dehydration deorganification test. So with another chemical you take out the organic. So then you have also first the organic and then the hydroxyapatite. And the other test, so these are three totally different protocols, right? From different laboratories and so on and so forth. Is etching. With etching we have to be careful. The idea is, okay, if I have a dry piece of bone and I burn it, then the organic part is burned and the mineral part is left. But it depends. If it becomes too hot, then you burn part of the inorganic part. So then you burn part of the mineral. And this took us 10 years to understand it, because there are these papers from the 40s and the 50s where they do it correctly. In the 40s and the 50s of the last century, the chemists were doing the tests. And then from the 60s and the 70s on, the biomedical engineers started to do it. And they wanted to be fast and so on, and they burned it quicker, and then everyone copied from everyone, let's burn at 600 degrees. And always the problem that these hundreds of burning tests never were inconsistent with the demineralization tests. Yeah? But now, since a couple of years, we understood, thanks to Jenny Wong, who I referred to, that okay, if we burn too much, yeah, then we always burn the mineral and we have correct to it. With this, we got back all the burning tests from the literature. Okay, having done this, the results is then, okay, let's plot something. Let's plot now the concentrations which we got out of the experiment, based on this relatively simple formula, but you know, to have the correct input and so on. Let's plot these concentrations as a function of the mass density, and the result is this here. So this is the mineral concentration as a function of mass density, organic concentration, and water concentration. And what we see, you know, these are bones tested between 1925 and 2003, and these are bones from whatever here, fin whale, horse, albino rat. So it's huge. It's almost everything, every age, every different animal, and so on and so forth. And what they are extremely precisely ordered in the end, right? And once you have the relation between this mineral and the mass density, then all the other curves are directly predicted. There is zero fitting here, absolutely zero fitting. And obviously there exists something. So mineral and collagen and water are not arbitrarily there. So there's a precise correlation. Well, then we might think, what might be the reason of this? How can we relate it to biological processes? So here we have the organic concentration over the mineral concentration, this bilinear relationship. So interestingly, first we have a situation for lower mineral contents or lower organic contents. We have, the more mineral we have, the more organic we have. Okay, this makes biologically sense in the sense that you say on the organic is built up by the cells, right? They build up more organic, and the cells also drive, the more cells you have, the more biological cells, the more mineralization you have. So it's what is called primary mineralization. It's driven by the biochemical environment on the tissue, and it's driven by the activity of the cells. Okay, that makes sense. But then we have so it's dominant in growing organisms. These are all rather young organisms, irregardless of children or rats or whatever. But then we have these other curves, which paradoxically is exactly the same slope, but with minus. Who knows why? I don't know. It's just experimental value. And they are dominant in aging organisms. So here this is something, you know, where the turnover rate becomes almost zero and so on. The biological activity is very, very slow at this branch. Okay, and this makes sense in the idea that this is basically to do with what is called secondary mineralization. So in this situation here, the mineral grows, triggered by the cells, but after a certain level, the osteocytes, which are other cells, they solute the mineral, which is too much. They don't let go the mineralization process beyond the threshold. But once they don't work anymore, the osteocytes, they don't dissolve this threshold, then we are basically in a geological system here. The biology has gone, has deposited it, and it's just growing until there is no place anymore. Right? And therefore, all of a sudden, it's inverse. Okay, that's an interpretation. Right? You can say, I don't believe it, I don't mind. What is interesting are the experimental data. So that was rule number one. Between organic and mineral content in mineralized tissue, there exists a unique bilinear relationship on which all different tissues, whichever you find in nature, fall onto it. Rule number 2. The question is now, if we look into the microstructure, where is the mineral in the extracellular bone? This was actually the oldest work, 10 years old now, the first thing we did on that. So as I said, we have in a piece of extracellular bone. So it was this piece, if you allow me to go back for a second, in this piece here. In this piece of extracellular bone, that's a transmission electron microscope. You have dark parts, which are the minerals, there's a lot of minerals, and lighter parts where there's less mineral and more organic and water parts. Okay, so our proposition, our model, so to speak, our structural model, which we can then formulate mathematically and check on different experiments whether it's correct, would be the following. So the white circles are the collagen molecules. Look on top of them, so they are long fibers. They are schematically looking into the room, pointing to the room. They build these higher units, organizational units called fibrils, so there is some space in between them, and they build these larger fibrils. And then there is some space where there is no fibril. Okay, so now we have two different extra, so to speak, extra spaces, which are outside of the organic matrix, which are related to two different scales. There's the extra collagenous space, which is outside the collagen molecules. This is everything what is gray in this image, if you look very precisely on each and every point. And then there is the extra fibrillar space, which is outside the fibril. Right? If you look at collagen or not collagen, but at the higher level of organization. And now our basic proposition is, okay, if the mineral precipitation is basically driven by the biological cells, so they make vesicles and so on, there's a whole branch in biology just dealing with this, then the very existence of a collagen molecule will not interfere very much. So that's the idea behind this structural model. So here the only problem the mineral has is the very existence of the collagen. If there is a collagen in space, it cannot precipitate there because there's no space, right? And therefore the idea is, we say that the concentration of minerals, so mass of mineral per volume, is the same in this extra collagenous space, so in this light gray space everywhere. This concentration is the same concentration as in the extrafibrillar space. And that's the thing we can mathematically write. Huh? So the mass of the mineral just in the extrafibrillar space divided by the volume, is it really identical to the overall mass divided by the volume minus the collagens alone of the extracollagenous space? Okay, then we can do a little bit of equivalent transformation. Huh? It's very primitive mathematics. And then we can formulate it that we have here volume fractions. So volume of extrafibrillar space over volume of tissue, and volume of collagen over volume of tissue. And of the other side we have mass densities, concentrations. So here we have geometrical properties, here we have chemical properties. Why do we do it like this? Because we hope that we can then test it, that we can prove this model by saying, okay, here we get access by the mass volume measurements of wet, dehydrated, demineralized tissues, exactly experiments which are very similar to the ones I've referred to before. So they would give us this term, and then this concentration ratios we would get from transmission electron microscopes. So we take images and compute on the images. And if they would give the same, if this would be equal, then okay, our idea is okay. So this is now the result. Now I leave a little bit of the mathematical steps, there are not too many. But based on the experiments I showed before, you can for each and every tissue compute this ratio, this amount of mineral which is outside the fibril. Okay, and then we have a lot of different tissues, and we see that between 50 and 90% are outside the fibril. So most of the mineral is outside the fibril, some is inside. And that would be the result of our idea that the concentration in the extrafibrillar and extracellular space is the same. And then we tested it on these three extremes. Turkey lactantum, which is very low mineralized tissue, and then medium mineralized tissue, and very high mineralized tissue. We tested this mass concentration in terms of OptiP densities from the TM, so we computed now on the TMs, and then we compared. And the comparison was really astonishing. It's almost perfect. So it means that, okay, up to that we believe to all these different experiments from different laboratories and so on, and this is what we published finally in 2003, is that we can really say, okay, this extra collagenous and oxalate concentration is uniform. So the mineral is just, the precipitation of the mineral is independent of the existence of collagen. And this gives us now the possibility to compute for each piece of bone So we take a piece of bone. From the rule number 1, we know from the mass density, which is easy to determine, how much mineral and collagen is there. Then from rule number 2, we can compute how much is in the fibrils, how much is out. Okay, let's go to the next pattern or rule we could find out, and let's go now for a second without mineralization, so, or let's say at the beginning of mineralization. If the cells put down a new piece of collagen, also in bone there is no mineralization, there's just collagen and water, and therefore I would say this part here is probably the most relevant for the more general scope of this workshop. So it would be relevant, I would dare to say, for any collagenous tissue, whatever it becomes afterwards. So the question is, how does this tissue, the structure of this tissue, change as a function of the water content? So the proposition we come up with is the following. So even if it's not bone, if you have skin, or if you have the parts of the eye or of blood vessels and so on, the collagen molecules, here they are again, they form these fibrils, these higher organizational units, and between the fibrils there's the extrafibrillar space. So that's a pattern you find in all collagenous biological materials. Okay, now we know if we, now the idea is the following. Once the extrafibrillar space, the big question is there a rule between the size of the extrafibrillar space and the size of the fibril? And our proposition is the following. So if the tissue is totally dried, then the extrafibrillar space is vanished. This is what a lot of people also from chemistry say. So then you have basically compact collagen. Because in reality they are not cylinders like this, they are very helical, complicated structures. So they can perfectly compact. So if everything is dry, then the fibrillar volume is equal to the dry volume. Then this is 0, so there is no extrafibrillar space. And then the simplest mathematical proposition, the one we do, is then that the extrafibrillar space just grows proportionally to the difference between the fibrillar volume and the dried tissue volume. So whatever I get in fibrillar space is proportional to my gain in fibril size due to swelling. That's the proposition. The question is now again, are there enough experiments, enough experimental evidence which we can put into a little bit of mathematics as to find out whether this is correct? First we say, okay, fibril and extrafibrillar volume together is the volume of the tissue, that we introduce tissue volume because this is what you can measure easily. And so again, it's very primitive mathematics here, tissue volume over dry volume, but this is what you can measure, is then our proportionality factor times this here. And now I want to check. Fibrillar volume, the fibrillar volume, and changes in fibrillar volume, so we are talking about a few tens of nanometers and so on, we can measure very nicely with X-ray diffraction spacings. Right? X-ray diffraction is used basically in material science and so on, mechanical engineering to test residual stresses, strains and so on in metals and so on. But these collagens, they have 1 nanometer distance, so it's exactly the same order of magnitude, and the X-ray diffraction spacings I will show in the next slide have a one-to-one correlation to what in mechanics we call strain tensors. Right? Okay, so we have an access to them here. And secondly, the water to organic mass ratio, this is also given in the literature. They measure how much organic is in the collagenous tissue and how much water. And from that we can translate it into this tissue volume. So again, we see we have 2 fundamentally different experiments. This is an experiment of experimental physics, right? And this is a classic experiment of fundamental weighing techniques. And if both fit together in order to confirm the existence of such a proportionality, then our rule was correct. So, coming back now to the question with the diffraction pattern, we do a little bit of continuum deformation theory, very basic. So the stretches, right? The stretches are the ratios of the lengths of a volume of a line element in a continuum in a deformed and undeformed configuration. So this is deformed, this is undeformed. With us, undeformed means so our reference is dry, and then everything is different stages of vibration. So these are the stretches, and then we know that volume changes, right, are related to the product of these stretches. And if you have then the product of the stretches, and the stretches themselves have to do with changes of characteristic lengths, and the characteristic lengths are exactly these spacings which are identified by the X-rays which you put through the tissue. So, based on continuum deformation theory, you can give a relation between this volume change you want to quantify and the things you have from experimental physics. And since these fibrils are not swelling very much in axial direction, but only in equatorial direction, so in transverse direction, it becomes a quadratic function of dW over dW dry. So diffraction spacing in wet over dry tissue. Okay, then we have the vacuum dried state. So if you take out all the water, when the material totally falls together, you still have 12% porosity. That's, I guess it's also valid for any collagen in the entire animal kingdom, whatever you want. It's always 12%, which is because of this Hodge-Petrushka scheme. So we have one molecule and then a certain space in the next molecule. And these spaces here in the middle, they are never lost. Yeah? You lose the spaces between the molecules, but not these long holes here. So that's the other thing.